Well, good evening. I'm glad that all of you are here, and it's got some friends in the crowd, and it's got the people from the class, so it's great. We have a diverse group of people. It's awesome. My name is Brent Bennett. I'm a graduate student in materials science working under Dr. Alan Bard. I'm going to talk about flow batteries today, but in a more general sense talk about energy storage on the electric grid. Y'all are a very diverse group, so I really looking to answer 3 questions with this talk. First of all, for the business-minded people here, why do we need storage on the electric grid? What are the economic drivers behind my work and all the other work that's being done in energy storage for the grid? For the engineers that are in the room, I'm going to talk about some of the technologies that are being pursued to meet that need. And specifically, we're going to focus in on flow batteries, because there's a lot of technologies. Flow batteries are just one small subset of the vast array of technologies out there. And then finally, we'll get to the more science portion of the talk, and we'll talk specifically about some of the work that's going on in my group and what we've been doing to push the frontier in terms of flow battery technologies. I'd be remiss if I didn't mention my 2 partners in this project, Netsuroy, who's right here in the room, and Jinho Chang, who just graduated. 2 of the smartest guys that I've ever worked with, and they've just been a real pleasure to work with them. So part of, when I get to the part of the talk where we talk about our technologies, just a part of it will be my project, and the other parts will be Net's and Jinho's project. So this is kind of a general overview. So why do we need storage on the grid, right? It's not just that our grid has an aging infrastructure and that we rely too heavily on fossil fuels and large fixed generating assets. There's the problem of the fact that electricity demand throughout the day varies quite a bit, and we're all pretty familiar with this problem, right? Everyone turns on their AC during the afternoon, and electricity demand goes up. Using your appliances, turn on your lights at night, and then when everybody goes to sleep, then demand goes down. So that's pretty much the only way that we can meet this, we can correct for this problem now, is we have generators that turn on and off, and they only run during certain parts of the day. So most of this demand in the upper half of the plot is met using gas generators that only operate during a part of the day. So we have these large fixed assets that are out there, and we're not using them efficiently. So if we could build energy storage that is cheaper than those generators, and if we can use it more effectively to provide these services that the grid needs, then hopefully we have a huge market. I mean, a lot of the market estimates out there that this could be in the tens of billions of dollars a year for grid storage. So it's a really big market. So again, why is there so little storage on the grid? Well, the big problem is that right now the energy storage options out there are too expensive. And the other side of the problem is that we've built our system around a generation-only model. So the transmission, generation, and distribution of electricity is built around a model where we're only generating. We don't have any storage. So we don't know how to price storage. We don't know how to incorporate it into the grid. And then we don't have the storage technologies out there that can really be competitive. It's a lot more complicated than the more simple example, which would be our water supply distribution. The way our water supply works is you have a treatment plant. It runs at a constant output all the time, and even though demand varies, right? So that houses and our businesses use different amounts of water during different times of the day, and over the course of the year as well. But we have a very cheap storage solution in terms of storage tanks, and there are water towers out there that is a very effective means for basically taking in excess water when there's less demand, and then letting that water out when there's more demand. So it's a very simple analogy, but the grid is a more complex animal, and so we're trying to do the same thing for the grid, but there's a lot that needs to be done to make that happen. So what are the storage technologies that are currently out there? Well, the biggest thing actually is pumped hydro, pumping water up and down a hill. That's 95% of the market right now is pumped hydro. It's a very old technology. The problem is that it can only be used in certain parts of the world. You need lots of water and you need big hills. So there's not very many places in the world where you can do that effectively and at the kind of low cost that you need for the grid. But as it is, it's a very simple technology, and in some places it's been used very effectively. Now, out of the other category, that other 5%, about a third of it is compressed air. Compressed air has been coming along in recent years. There's a lot of work that's been developed on it. And basically what you're doing is you're compressing air inside a salt cavern or a tank, and then as you let it out, it turns a generator that will feed electricity out into the grid. So another big one is thermal storage, basically heating and cooling water or other materials. We have a big thermal storage system actually in downtown Austin. There's several buildings have a piping system connected together that provides extra cool water for air conditioning during the hot summer days. So that's a very simple thermal storage system. And then the other third, which is what I'm going to be talking about, are the battery technologies. And now the battery technologies right now are a very small part of the market, but over the next 10 to 20 years we think that it's going to become a very big part of the market. And so that's why we're doing a lot of research and development in that area. So basically, what are the battery technologies that we're looking at for the grid? Well, there's a lot. Okay, these are just a sampling of the technologies that are in commercial development right now. If I were to put up a list of technologies that are being looked at in the academic world, you could probably triple the size of this list. So I just said, okay, well, what can I fit onto one slide, and we'll throw that much up there. The way I kind of classify, these technologies are, first of all, you have the old school batteries. Companies that are trying to take upgraded versions of lead acid, nickel metal hydride, nickel cadmium, and make them more efficient, cheaper, longer lasting for the grid. There's some people that think that this can be done. I'm not a big fan of it just because what's been tried so far hasn't really been that effective. For example, Extreme Power tried to use advanced lead acid batteries, and that eventually they found that the batteries didn't last long enough. You couldn't use them in most grid storage applications, and so they eventually went bankrupt because of that, because they didn't have a good battery technology. So there's again, people trying to do that, but there's not a whole lot of more people are starting to go towards newer technologies. What's really coming to the fore now are large format lithium-ion batteries. Lithium iron phosphate, which is the material developed right here at UT. I think it's now our second largest source of patent income. That's being used a lot now in stationary storage applications, like smaller scale applications, backup power for cell phone towers, electric scooters, things like that. But there's people that think that it can be made even cheaper and put on the grid. So that's definitely coming along. We're seeing more of that. One area that I think has really a lot of potential are high temperature batteries. GE just spent about $200 million to build a plant for sodium nickel batteries, and we'll see how that goes. They're going to start off in the backup storage market and then try and scale it up to the grid storage market. Some of you may have seen a TED Talk by Donald Sadoway about liquid metal batteries. We actually have Huayi here, and who's in my group, who worked on that project. And the liquid metal batteries, high temperature batteries, are very different from traditional batteries, and they're very cheap, very simple. By taking your temperature up to 300-400 Celsius, you can really get a lot of cool properties, a lot of opportunity there. Another big area are what I call lithium-ion analogs. So you have like sodium-ion, potassium-ion, magnesium-ion. Basically, they work just like lithium-ion batteries, but you're using larger ions, so the batteries become much bigger. But essentially, they work the same way as your typical lithium-ion battery, and they're a lot cheaper. And then finally, the final category, most of what I'll talk about today, are flow batteries. NASA developed the first flow battery back in the late 70s. Used iron and chromium. And there's a company called Enervolt that's trying to commercialize that technology right now. The all-vanadium flow battery was developed in the 80s in Australia by a group at University of New South Wales. And that's probably the most popular technology right now. And there's also zinc bromine is also a very popular chemistry. But there's lots of others, dozens and dozens of proposals that are out there. But those are the three that are really being commercialized right now. So just to give you a sense of the kind of scale that we're talking about when we talk about flow batteries and other types of energy storage technologies. This is a demonstration unit, a 60 megawatt hour demonstration unit out in Japan. It's one of the largest flow batteries that's been built so far. And again, I mean, that's a really big piece of equipment right there. And they'll get a lot bigger than that when you really start to see flow batteries and other technologies coming into the fore. This will be a small unit, because when we're on the grid, we're talking about gigawatts. We're not talking about megawatts. So this is megawatt scale, so it's just going to get that much bigger. So when we're doing research and development of these batteries, we have to think really hard about how do we scale these things up, because we're not making little cell phone batteries and making hundreds of them. We're making really big batteries. So if we scale this down to our prototype that we have in the lab, and this is a battery that mostly Net's built. I helped him a little bit with it. It's just kind of to show you just the different parts of a flow battery. Okay, so this part right here, that's the battery cell itself, and that's where the reactions take place. And you can see there the red and the black wires. Those are the leads that go off to carry the current in and out of the battery. And then, so what happens is when you run the battery, you have your active material that's stored in these tanks right here, and when you turn on the pumps, and so the pumps pump the material through the battery itself, and that's where the charge and discharge reactions happen. And from that, you get your current. Basically, depending on how you polarize your battery, you're either charging it or you're discharging it. You're either putting current in or you're getting current out of it. Okay. And so that's basically what a battery, a one-cell battery looks like. And when you scale this up, basically you just take those cells and just stack hundreds, thousands of them together, and you get, if you go back, these little beakers here correspond to those huge tanks that are in the center right there. Okay. So it's the same basic design, but it looks totally different once you scale it up. But that's what we're trying to do. So the advantages of flow batteries, probably the biggest advantage is that they're very modular and very scalable. Again, I mean, if you want to scale up a flow battery, you just take thousands of little cells and stack them together. Now you have to design them differently. You have to make a lot of changes, but it's the same basic design, and you can build a flow battery such that you can either, if you want a lot of energy storage, you build big tanks. You put a lot of material in those tanks. Okay. But if you want to get a lot of current out of your battery, then you build a lot of cells. Okay, so you can basically your energy storage and the amount of current that you get out of your system are decoupled. So you can basically build it to fit the needs of whatever grid application you're talking about. Okay, so that's a really important thing. A lot of battery technologies do not have that kind of modularity, and so it's hard to get them to fit into a certain application that's needed on the grid. The other thing is that they use very low-cost materials. The solutions that we use are for the batteries are very cheap. Use very cheap materials. Water, iron, chromium, acids. Very cheap materials. But we still need to make them a lot cheaper. There's some parts of the battery cell itself that are still quite expensive. So that's one big area of research, is trying to use less materials and make those materials cheaper. The other thing is that flow batteries are very long-lasting. Your cell phone battery might die in a couple of years because there's a bunch of failure mechanisms that cause the battery to lose capacity over time. Flow battery, if it loses capacity over time, well, you can just replace the solution. So you can go in and replace certain parts of the battery. You don't have to throw it away. So they can last as long as you want them to last. There's just a certain maintenance cost that you're trying to minimize over time. So low maintenance is a critical factor. So again, the economics of grid storage, you have a large upfront capital cost, and you're trying to pay that back over time by providing services to the grid. Okay. Now we're looking at a payback. We want to see payback in terms of like 5 years or less than 10 years, and right now it's a lot more than that. So we have to bring down the capital cost of batteries. So that's a big thing when you're talking about our research and development of flow batteries. We want to use cheaper materials, less of them. Okay. And another thing, in order to get to make the batteries useful for the grid and to get a lot of to provide a lot of value in terms of the services we're providing, we need them to be able to charge and discharge quickly. We need them to have very high energy efficiency. We want the amount of electricity going in to be the same as what we get out. We don't want to get out only half of what we put in. That's really important. And finally, we want low capacity loss so that the batteries last a long time. And then also we need long-lasting components. So now we switch over to the more science part of it, talking about what my group's working on, and looking at it in light of what I just showed you there. What we're trying to accomplish in our research. Okay. So this has been Netz's chemistry, what he's been working on. He uses complexes of iron and cobalt and strong base. Now, almost all the flow battery technology you see out there right now work in strong acid, sulfuric acid, hydrochloric acid, things like that. But what Netz has developed is a chemistry that operates in 5 molar sodium hydroxide. It's a strong base. Okay? And he uses an iron complex with an organic molecule called triethanolamine, and then cobalt with a derivative of that. And these are very nice, efficient reactions, very reversible. The cell itself is very long-lasting because there's minimal crossover. So the way that a flow battery loses capacity because either, in this case, the cobalt would cross over to the iron side, or the iron would go over to the cobalt side, and so you lose capacity that way. And this battery has almost none of that. Again, very unique among flow batteries in that respect. The problem is that the energy density is very low. So we need really big tanks for this thing. And we need a better membrane as well. The membrane that separates the two sides of the battery is a really important component. And that's something all the membranes have been developed so far for strong acids, not for bases. So we need something that works really well in a strong base. The other project what Jinho was working on was tin bromide complexes. The tin-2, tin-4 reaction is very famous in electrochemistry. It's also famously irreversible. What I mean by that is that the potential to run the reaction in the charging direction, which would be the direction going to the right, is a lot higher than the potential, well, lower, but the cell potential is a lot higher than it is to run the discharge reaction. So you basically, that goes directly into your energy efficiency. So you're going to get a lot less electricity out of the battery than what you put into it when you have an irreversible reaction. So Jinho spent his whole PhD trying to figure out how that reaction goes and how to make it more efficient, more reversible. And he found some good ideas to help future researchers get along in that regard. The big advantage of this battery is that it would cheap materials, high energy density, and you use the same solution on both sides effectively. So that allows for different kinds of battery designs, cheaper designs, and we're really hopeful that somebody can take the reaction problems and work on them a little more, and maybe actually develop a good prototype. And so finally, we have the project that I'm working on. I'm basically, instead of trying to use cheaper materials, I'm going the opposite direction and trying to use less of those materials. So I'm trying to create a flow battery that has very high energy density. The idea being that if I create a battery that has 5 times the energy density of a typical battery, I can use 1/5 the amount of materials. Okay? So it's kind of a bit of a different tack. And the way that we're going about it is we're using 2 liquids, bromine and nitrobenzene. They're what we call redox active liquids. Basically that means that they're liquids, but they undergo chemical reactions, and so you can use them as both a solvent and an active material. Okay? And so basically we're trying to create a battery where you're not just electrolyzing part of the material that's in the solution, you're actually electrolyzing the whole solution. So again, you're using all of your materials so you don't have to use as much of it. Okay? So these are more expensive materials, but we're hoping to use a lot less of them. The big problems with this battery is that you're using organic solvents, so your conductivity is very low in this battery. When you have a lot of resistance inside a battery, again, that creates efficiency losses. You put energy in, and a lot of it gets wasted in the form of resistance, and you don't get as much out of it. So that's one big problem I'm trying to solve, is to find a good salt to go in the battery to make it conduct really well. Hopefully we can do that. The other problem I'm working on is that the bromine electrode is also very irreversible in these solvents. So I'm trying to, again, do the same thing that Jinho did, trying to make that reaction more reversible and more efficient. So that's it. And I would just like to say that I hope that this quick little bit give you an idea of just what we're trying to do, what we're pursuing in terms of storage technologies, and then also what we're doing specifically in this group to advance the field of flow batteries. So thanks for your time.
Now we have a couple minutes for questions.
Hello. Yeah. Enjoyed your presentation. I have a question. So when you say you try to make these reactions quicker, is that involving any new sort of chemicals that you're adding to the process? Is it completely in terms of material interactions? Like you just try to layer it and you try different kinds of textures and that kind of thing?
That's a great question. So that's one of the things that that Jinho worked on during the last part of his PhD. Basically, there's two things you can do. First of all, you can develop catalysts. Okay, catalysts make reactions go faster. And so that's really the big area. So all these electrodes that we use are carbon, but maybe it's possible that you can develop a cheap catalyst that you can put on the carbon electrode, and thereby make the reaction faster and more reversible. Okay. The other thing you can do is you can kind of change the conditions. You can heat it up. We found that was really effective. So you can heat up the cell from room temperature to say 80 degrees Celsius, and that makes a big difference. So things like that, you can either add a catalyst or you can change the conditions inside the battery.
I know you kept saying that a big concern was trying to keep the materials cheap. I was just curious if there was maybe a situation where somebody found a great design, but the U.S. would have had to import most of the materials, so it wasn't feasible to scale up or something like that.
Yeah, no, that's a good question. I mean, I think that the biggest area where that's true is in people that are trying to develop lithium-ion batteries for grid storage applications, because those are more expensive. When people go into the flow battery realm, you're pretty much if the material's too expensive, you're not even going to look at it. But there's some people that are coming from the lithium battery world where you have more expensive materials, and lithium. Again, we import most of our lithium, and we import most of our lithium-ion batteries as well, and as whole parts from China or other places. So so it's mostly a problem in that realm. But it is, I mean, that's something that for us building flow batteries, we go in from the beginning and say we have to use cheap materials. If it's not cheap enough, then we don't even consider it.
Thanks, Brent. So my question is about, you mentioned how large the batteries that you're developing, you're trying to make them gigawatt scale.
Yeah.
So with the onset of a lot of distributed generation and microgrids, do you think that that's really where we should be going in terms of batteries, or do you think that a better application or more an economical application would be smaller at the community scale?
Well, that's a great question, yeah. And this ties into Aaron's research, just so y'all know. But no, it's really going to be a dual problem, because we're going to have, for far into the foreseeable future, even as distributed generation comes onto the grid, we're still going to have a lot of large fixed assets. Even the renewable energy that's coming out on the grid now, and I didn't really mention renewable energy as part of this presentation, but when you add renewables to the grid, not only do you have variable demand, but also variable supply. And so renewables are what really will bring distributed generation to the fore, putting solar panels on your roof and things like that. And so yes, in that case, then yes, you need smaller scale storage, and that'll be really important. But then we'll still have the greater demands of the grid that will need to be met by the larger scale storage. So it's going to be a little bit of both. That's the answer. Any other questions?
I was wondering about when you're talking about heating up the batteries to make them more effective. Firstly, do they have to stay heated up throughout the length that they're storing that energy? Okay.
Are you talking about the high temperature batteries, or about how we can heat up batteries to make reactions more efficient?
I mean, at first glance, I sort of thought they were similar or maybe the same thing, but
there's a little bit. Yeah, there's a little bit of similarity. Yeah, when you heat a battery up to high, when you heat a battery up, then the reaction, then not only do you increase the conductivity, right? You make the ions inside the battery move faster, so that the conductivity goes up, and so you're lowering the resistance. But then you also make the reactions go faster, right?
Right.
So that's So both of those cases are true. So in a traditional, in a water-based flow battery, you can maybe heat it. You can maybe try and heat it up to some temperature below 100 Celsius, and then you can somehow maybe make it more effective. And yes, it has to stay heated the whole time. Otherwise, you're going to lose those gains that you make by heating it up. In case of the high temperature batteries, the really high temperature ones, that are above 300 Celsius, say, then those have to remain hot all the time, just because if they cool down, then the metals are going to solidify and the battery just won't work, right? Mm-hmm. And so basically those batteries are designed to where you have two liquid metals with a molten salt in between them to separate them. Okay.
So then, so the sum of, storing that energy and whatever the benefits are from that, but then also considering the cost of heating it up.
Right.
So what is the?
How
would you compare?
That's an interesting question, and that's a lot of work going into that. What they've found in a lot of cases is that in the high temperature batteries, you can actually use the resistance of the battery can work in your favor, because when there's resistance in a battery, that gives off heat. That's how you're losing that energy in the form of heat. So if you can build a good insulator around the battery, it can effectively heat itself a little bit. There's obviously the cost of energy that it takes to heat it up initially, which is substantial. But especially in the batteries that GE is developing now, they say that they can almost heat themselves. It's a very interesting design. Lots of new things can take place when you heat a battery up.
Anybody else? We have time for one more question. All right, let's give it up one more time for our speaker.
Thank you. Yeah, you can just tear it apart or pull it over your head.
All right, hi everyone. I'm just going to introduce myself again. I'm Sean Wood. I'm a third-year PhD student in chemical engineering. I work for Drs. Buddy Mullins and Adam Heller in the Chemie department. And today I'm going to talk a little bit about my research into lithium-ion batteries. Specifically, this material I've been using, lead telluride, which is geared more towards consumer electronics. And so what we do in our lab in general is we try to take materials at the nanoscale, like these nanoparticles you see up here, and then turn them into materials suitable for applications at the macro scale, such as electric vehicles, consumer electronics. Got some grid storage shown here. So just a brief outline of what I'm going to talk about. I'm going to give some introduction and motivation for why we look at lithium-ion batteries and what motivates us to want to do research into this field. How lithium-ion batteries work. I have a little schematic to show you that kind of shows like where the ions are moving and things like that. Then I'll talk about the current material that's used, graphite, and why we want to get rid of that and replace it with something new. The material I'm choosing to work with is lead. Then I'll talk about the characterization, synthesis and characterization of the material that I'm working with, which is a telluride of lead. And then I'll get to the actual meat of the presentation, which is the electrochemical results, which shows how this material actually performs in a lithium-ion battery. And then from the lab scale ideal situation, like what it would be like to use in real batteries. Then I'll close it with some conclusions. So why do we look at lithium-ion batteries? Probably everyone in this room has a lithium-ion battery in their pocket right now. And so if we look at world lithium production since lithium-ion batteries were introduced in 1991, we can kind of see how their use has kind of exploded over time. Starting with things like camcorders back in the early 90s and laptops, to iPods and smartphones, and now tablets. In the future, we're also going to have things such as electric vehicles and grid storage, and that could cause this to go up even further. So there's a lot of demand for lithium-ion batteries, and it's only going to continue to grow. And so we need to improve the technology. The battery that's in your pocket right now has used the same two materials pretty much since 1991 when Sony introduced them. And so we've kind of reached the limits of what they can do. So this is kind of a schematic of what these batteries look like. You have two sides, the anode and the cathode. The cathode's on the left, and there's an aluminum current collector, and on top of that is a mixture of lithium cobalt oxide particles. That's the most common. That material was developed here at UT by Dr. John Goodenough. And then there's these sort of conductive carbon particles that form a bridge that connect the active material to the current collector, which is where the electrons go to move back and forth between the two. On the right side, we have the anode with a copper current collector, and the active material there is graphite. So this is the side of the battery that I work on. We're trying to replace these graphite particles. And so when you charge a battery, you can see we have a dead battery here at the bottom right. When you charge a battery, what's going to happen is lithium atoms are going to dissociate from the lithium cobalt oxide into a lithium ion that's positively charged and an electron that's negatively charged. The lithium ions will travel across the battery through the separator to the anode, and the electrons will travel through a circuit, and they'll meet up in the graphite, and that'll charge your battery for you. When you actually use your battery in some sort of electronic, such as your phone or your laptop, the opposite occurs, and the lithium ions go from the anode to the cathode. So what are some of the problems with graphite that we use currently? I'm sure we've all experienced this here, like this lady's doing, where we have our battery that our phone runs out of battery and dies at just the worst time, and then you need to recharge it, and it takes 3 hours, and we just really wish that it would last longer and charge faster. So we're looking at new materials that will help that happen. On a more technical side, graphite has a really low lithium insertion voltage. So what this means is that it gets really close to the potential of lithium itself. And so lithium can start growing on here and form these kind of needle-like dendrites, which will pierce the separator, cause a short, and that can lead to fires, which we've seen in the news and is very bad. So here's kind of a comparison of graphite, which is currently used, and then the lead that I'm trying to use to replace it. So the two methods of lithium storage are fundamentally different. So with graphite, you have these graphene planes that are kind of parallel to each other, and lithium ions kind of insert between them, and that's how they're stored. And so when that happens, you only experience about a 10% shift in the volume. You can only store 1 lithium ion per about 6 carbon atoms, and this gives you a pretty low gravimetric capacity of about 372 milliamperes per gram. Also, graphite isn't very dense, and so if you look at a volumetric capacity, it's pretty low also. Lead has a completely different method of lithium storage. It actually alloys with the lithium, basically forming chemical bonds and creating a whole new crystal structure. So this means that it can take up a lot more lithium. You can get 4.5 lithiums per atom of lead, whereas only 1 atom per 6 atoms of carbon for graphite. This leads to a massive volume change, though. When you insert the lithium, the particle goes from one size to a size 323% larger. And this has its own set of issues. But because you can insert so many lithiums, you get a much higher capacity of about 582 milliamperes per gram. And because lead is so dense, your volumetric capacity is actually more than 8 times higher than that of graphite. And so now I'll get into the synthesis. As a grad student, I like to find the cheapest, easiest, fastest way to make a material. And so this is a pretty easy method I found for making the lead telluride that I wanted to test. So you basically have a dissolved solution of tellurium metal with a reducing agent. And then you add your lead dropwise to that. So you have Te2 minus and Pb2 plus. That reacts for a little bit and forms this nice black lead telluride powder. So I ran X-ray diffraction on this powder just to verify that I had what I think I had. So my spectrum is this blue line. If you compare that with the reference spectrum for lead telluride, which is the green lines, you can see that the peaks match up pretty well. So I'm confident that I got lead telluride. And then I did a scanning electron micrograph, which is in the bottom right of the particles. And you can see that it's composed of 30 to 40 nanometer, roughly spherical particles. Typically in batteries, smaller is better in terms of performance. And so these are pretty small particles. And you'll see later we get pretty good performance out of them. And so now I'm about to jump pretty deep into the science part of this. But first, let me talk about safety. In the chemical engineering department, we like to be pretty safe if we can. And so lithium and sodium, we also do a little bit of sodium-ion battery work. These are both materials that degrade when they come in contact with air. And if they come in contact with water, they give off hydrogen and sometimes fire. And then the electrolyte salts that we use in the batteries can hydrolyze to form hydrofluoric acid, which is not only a really strong acid, but it literally leaches the calcium out of your bones, causing a pretty horrific death. And so the electrolyte solvents we use are also flammable and toxic, not fun to breathe in. So what we do to circumvent all these problems is we build our batteries in an argon-filled glove box, which you can see pictured behind me there. So basically when I'm in this glove box, I have 3 layers of gloves on. I've got a nice thick layer of plexiglass in front of me, hiding me from all of these terrible things. All right, so now the science. So my lead telluride I compared to a more standard oxide, lead oxide. And so these are the reactions that you see here. You don't have to know exactly what's going on here, except that as you go down in the reactions, that's when you go down in voltage. You get closer to a voltage of 0 as you go down. One thing to note is that the lead oxide, the very first reaction, is irreversible. So once you go from lead oxide to lithium oxide, that reaction is irreversible and doesn't go back. So you lose a lot of capacity there. With lead telluride, once you form lithium telluride, you can actually extract the lithium back out of that, and so you gain some extra capacity there. And the main reason for this is the difference in electronegativities between the two. It's a pretty high difference for lithium and oxygen, but it's lower for lithium and tellurium, so you're able to separate those two. And then basically the last 4 reactions for each are pretty much the same. That's just your lithium insertion into lead. That's how you get your ultimate 4.5 lithiums per lead atom. And one thing to notice is that while that reaction is taking place for each set of reactions, you have lithium oxide present or lithium telluride. So once you convert that oxide or telluride to lithium oxide or lithium telluride, they stay for the rest of the lead insertion reactions. And so we can see this graphically with these cyclic voltammograms. Basically, anything to the left of 0.7 volts is those lead reactions that I showed you, the last 4. And so you can see those are pretty similar for both materials. Anything to the right of 0.7 is either tellurium versus oxygen. And so you can see here this hump that appears in the first cycle for lead oxide, but it doesn't appear anywhere else. That's that irreversible reaction of lithium oxide. And so if you kind of integrate this curve, that's a lot of capacity you're losing on your first cycle. For the lead telluride, you can see those humps stay there the entire time in subsequent cycles. And so you're able to extract that lithium back out of your tellurium. You can also notice that with the lead oxide, the peak height decreases as you cycle, whereas it stays pretty much constant for the lead telluride. This has to do with the reversibility of the reaction. And so with the lead oxide, you're losing capacity for each cycle, which you don't want your battery to do. The lead telluride seems to perform much more stably. And we can actually see this more easily if we look at galvanostatic cycling. So for the lead oxide, we cycled it at a pretty slow rate where we charged it in 10 hours and discharged it in 10 hours. The lead telluride we did a little more intensely at 5 hours charge, 5 hours discharge. And that's what these C rates here down at the bottom are. So C over 10 corresponds to 10-hour charge, 10-hour discharge. C over 5 is 5-hour charge, 5-hour discharge. And you see that the lead oxide has pretty rapid capacity fade. So we want these lines to be as straight as possible. In an ideal battery, it would be perfectly flat for thousands of cycles. You may ask why I only have 100. I could do 1,000 cycles, but I would be here for many more years than I would like to be. And so 100 cycles is kind of enough to show that, hey, this deserves further research. And so you can see that there's 2 lines up here. And what that is if we go back, for the lower line, this one here, the black line, I'm only looking at lithium insertion into the lead, which is this left part. But if I include the tellurium reactions over here, that's what this upper line is. And so you can see with lead oxide, I did the 2 different voltage ranges and didn't get any difference in capacity. That's because that first reaction was irreversible. But with the lead telluride, it's not irreversible, so we actually get extra capacity out of there. And you can see that it's pretty flat for both. So now if we want to try it at a little bit higher rate, we can kind of push them to see the limits of how fast they can be charged. So for the lead oxide, we went up to a maximum rate of 1C, which is charging in 1 hour, discharging in 1 hour. And you can see that there's capacity fade through all the different C rates. It flattens out a little bit at 1C, but once you return to the slow rate at C over 10, there's capacity fade yet again. With the lead telluride, we go all the way up to 10C, which is charging in 6 minutes and discharging in 6 minutes, which is pretty fast for a lithium-ion battery. Graphite itself can only go up to about 1C before it starts suffering damage. And you can see that we actually maintain a little bit of capacity even at that high rate. And even more impressive, we go back to the original capacity once we go back to the slower rates. And so if we take one of those cycles for each of the different C rates and compare their differential capacity profiles, so each of these pairs of peaks, so like these 2 here and these 2 here, correspond to one of the reactions, one of the lead reactions that I showed you before. So an ideal reaction, they would be really close together. The farther apart they get, the more non-ideal it is and the harder it is to make that reaction occur. And so what we want to see here is for these 2 peaks to be really close together and for them to stay close together as you increase your C rate. We can see here for the lead oxide that the peaks kind of shift rightward, or shift wider. Rightward on top and leftward on the bottom. But for the lead telluride, there isn't much shifting. as we go. And so if we put little bars here, where the left side of the bar represents the bottom peak and the right side represents the top peak, we can get a graph like this. And this, I think, makes it more clear which of these materials is actually winning the competition. The lead oxide, you can see, starts out relatively small, but as you increase to not even that high of a series, 1C, the difference between the peaks gets much larger. And here, bigger is not better. The lead telluride only increases a little bit as you increase in C rate. And so what this is saying is that the reactions are much easier to perform with the lead telluride. So the only difference between these two is that one system has lithium oxide, one has lithium telluride. Otherwise, it's just lithium inserting in and out of the lead. And so we kind of have some theories as to why the lithium telluride is helping the system like this. And one is that lithium telluride itself is a superionic conductor. What this means is that on a technical level, it has a ionic conductivity higher than 10 to the negative 2 inverse ohms, inverse centimeters. What it really means is basically the lithiums are able to diffuse more rapidly through that crystalline lattice to reach its destination. And so there's been some theoretical computational studies done on lithium telluride to see if it's a superionic conductor. And those say that they are, but there's not been any experiments done. So some of my future work involves actually right now creating tellurium films and then trying to lithiate them and see to measure this ionic conductivity to confirm that it is in fact a superionic conductor. And so if we go back to that 100 cycles at a constant rate, we look at the differential capacity profiles. One thing I want to point out here is this red and black peak. So basically, it's been shown in the literature that once all the lithium is removed from the lead and once all the lithium is removed from the tellurium, each lead and each tellurium atom recombine into that lead telluride crystal structure. And that's what this peak corresponds to. But you can see that it's completely gone after about 5 cycles. And so we're kind of wondering why that happens. One theoretical reason that we have is just that the two different materials have much different volume changes as they expand. So first you insert your lithium into the tellurium, and that undergoes a 204% volume change. And then you insert it into the lead, and that undergoes a 323% volume change. And so just the fact that they're expanding at different times and contracting at different times, and the magnitudes are also different, it basically just destroys this crystal lattice here, and the tellurium and the lithium can't recombine into a single crystal structure. However, that doesn't seem to have much impact on the performance because we still got really stable cycling. I'm going to be working with Kyle here to do some more experiments to find out whether or not this is actually happening and to try and find out the exact mechanism of this breakdown. So now we get to the fun part, which is what would this look like in a real battery? So I mentioned before the fires that can be caused by graphite having too low of a lithium insertion potential. And so graphite's potential is this red line here. So you can see for my battery, the average lithium insertion potentials are much higher. In this lower voltage range, it's about 0.3, and in the upper voltage range, it's about 0.7. Both these are significantly higher than the lithium plus redox couple, and so we won't get those needle-like dendrites, and we won't get the terrible flames that we saw before. And so what if we want to put this in an actual battery? So I have a Samsung Galaxy S3. It's got 2100 milliamp hour capacity. If I wanted to take that battery and replace all the graphite in it with my lead telluride material, I could charge it and discharge it in 30 minutes, and the weight would only increase by about 6.5 grams. That would be like taping 3 dimes to the back of my battery, which I think is a pretty good trade-off if I can charge it in 30 minutes. And so how much would this cost? So this is a good news, bad news sort of situation. This much lead telluride costs 14,000% more than graphite, but this is because graphite is cheaper than cheap, and so what this actually translates to is only about $1 increase in the price. So to sum up, the lead telluride performs better than the lead oxide by nearly all the metrics we tested, especially stability and rate capability. You can see over here on the right, just to remind you. We think this is because the lithium telluride acts as a superionic conductor. It reduces the overpotential, which makes that reaction easier, even at higher rates. And so in a real battery, it would only marginally increase the weight, and you could charge it in 30 minutes. And so with that, I'd like to thank my advisors, Buddy and Adam, and then Kyle and Paul from the battery group, as well as my entire research group, and then the IGERT Fellowship and the NDSUG Fellowship for funding. And with that, I'll take any questions.
Does anybody have a question?
I know nothing about engineering, I know nothing about chemistry, so I didn't understand most of your presentation. My background is in business and finance. So what interested me is the last part where you said it would cost only $1.06 more and a little more weight to charge your battery in 30 minutes versus 3 hours. Why wouldn't anyone do that?
So there are engineering difficulties just going from a material that you have in like a science lab to like an actual battery. I published a paper on this. It's one of 2 papers for this material, and so I just think it's not much is known about it yet.
So there's potential perhaps in the future that this would happen, but it's just kind of translating from the lab to real life right now.
Yeah, it's sort of like all engineering difficulties, all engineering problems. Like you have the chemists and the science in the lab who say, oh, we have this great thing, and then you give it to the engineers and like, well, we can't actually make this work. Yeah, so it could be done, but more work would be needed to get it to actually function in a real battery. Mine was just if you replaced it with my data, if you used my data to replace the material, what would that theoretically look like?
I have 2 questions. One question is that you used the lead and the terbium as the anode materials. So during the discharge or charge process, there were 2 platos, right? The potential platos should have 2 platos, right?
Well, so that goes back to the equations that I showed.
Yeah, I think so.
Yeah. So you can see for the lead, there's 4 plateaus alone.
Yeah.
And then for the tellurium, there's going to be 2 plateaus.
Yeah, so that means your battery doesn't have a constant voltage during the charging, discharging process. So how do you solve this problem? Because you know when our cell phones use the battery, they always have the constant cell voltage, right?
Mm-hmm. Right. So what I've heard is that applications that require more power, such as electric vehicles, do require that constant voltage, but low voltage applications such as cell phones and things like that can tolerate small changes in voltage. And then that goes back to the engineering problems of how do you actually get it to measure the small changes in voltage and account for that. But I think that consumer electronics are able to tolerate those small changes in voltage.
Okay. And the other question is that when during the charging process, the lithium was alloyed with the lead or terbium, and the volume expand around 300%. So when the lithium leave a de-alloy from the alloy materials, so your lead or terbium will be porous. So I think you can observe from SEM or TM. So that means when you charge and discharge, the volume expand. So if in the future, if you scale up your battery and your alloy materials will expand step by step, that may be short the cell. So have you considered these programs? Okay.
So the way the electrodes are made, we have, it's kind of a porous structure, and so there's kind of some room for the materials to expand and contract within that porous structure, just in the film itself. So there's been a lot of research done into the expansion and contraction of things like silicon and germanium and tin. And so they don't really become porous, I think. They kind of sort of expand and fracture, leaving still solid materials behind. I think that it wouldn't really cause problems with shorting as long as your separator is decent enough. That'll prevent electronic contact from one side of the battery to the other.
You mentioned some of the safety concerns associated with some of the materials you were working with. One thing I was wondering was about the life cycle environmental impact of the new batteries that are being developed, and sort of what issues would arise if these batteries leak, and whether battery recycling research is being developed in parallel with what you're doing.
So that was actually one of the reasons I chose lead, was because there's already kind of that infrastructure in place. Like 85% of the lead in the country is used in lead-acid batteries in vehicles. And there is a pretty, I think something like 80 to 90% of that lead is recycled. So the lead recycling is already very good for batteries. And another thing is that as we start moving towards electric vehicles, we're going to be getting rid of the conventional lead-acid batteries. And so a way to prevent that extra lead from like going into the environment or something would be to use it to make these batteries instead.
Any more questions? All right, well, let's thank both of our speakers, especially I want to remind everybody as well and encourage you to come on out next Monday. We're having a talk here in this auditorium at 4:45 with the esteemed Arnulf Grubler. He's coming all the way from Yale University, and he's going to speak to us about energy and urbanization. It'll be our last official Li₂Te Energy Symposium talk of the semester, so please try and make it out if you can. Thank you all.